Hi, class. This is Mr. Hart. In this podcast, we're going to go over the topics we covered during week two of the properties of matter unit. Okay, so we started off by talking about different types of matter, different groups, and first of all, we looked at elements. So an element is just any type of pure substance. Okay, you can't break them down into something simpler that still holds its chemical properties. Okay, and you can't combine anything together to make an element. These are the purest types of matter. Okay, and so some examples are things like gold and mercury and copper and helium. These are things we all have to, uh, for all these things, we have to either mine them or find some type of storage for them. Okay, because we can't just create them out of thin air. For example, gold. Scientists back in the old times used to spend years and years in a practice called alchemy just trying to make gold, but they didn't realize it was an element, so you can't just make it from something else. Okay, so there are 117 known elements right now. 92 of those are natural elements that we find on the earth from rock, soil, air, water. Okay, these things we don't have to uh, artificially create in a lab, um, but 92 of them are naturally made. Okay, the rest have to be made through nuclear processes, and right now we have about 117, and that number is growing. Okay, so you might also wonder the relationship between atoms and elements. They're pretty much the same thing almost, but if you think about it like this way, an atom, okay, in an element is going to be the same no matter which one you pick. So all the atoms in a single element are going to be the same type. Okay. For example, if you saw a sample of hydrogen, all the hydrogen atoms are going to have one proton. That's why they're hydrogen atoms. So in an element, they're all going to be that one proton type atom. Okay, that's the relation between atoms and elements. Then we did a small simulation showing this. Um, Again, that's on the PhET's website if you want to look it up. It's called Build an Atom. Then we talked about element symbols. Okay, so every element has a specific symbol. It's either one or two letters long. It usually comes from the Latin or Greek name of the element. Okay, and if you look at it, for example, we have aluminum here as an element. Its symbol is A, capital A, lowercase l. Okay, calcium is a capital C, lowercase a. Gold is a capital A, lowercase u, because the Greek word for gold is aurum. Okay, so every element has some type of symbol that we can use to represent it chemically. Okay, so then we thought about this question: How come if we only have 92 naturally occurring elements, why can we form so many things in the world around us? Okay, and that comes because of compounds. When we take these elements together and we combine them, we get chemically uh, unique properties. We get new materials when we combine these elements together. So, what is a compound? It's formed when we have two or more elements chemically combined together, okay, in some type of chemical reaction. So, when this new compound forms, it has different properties from the original element. For example, if you've ever eaten salt, table salt, if you've ever put it in your food, well, salt is made from sodium and chloride. Well, sodium is poisonous by itself, and chloride is poisonous by itself, or chlorine is poisonous by itself. When you combine the sodium and the chlorine together, you get sodium chloride. And sodium chloride is salt, so we can eat it. So it's kind of strange that, the two elements themselves, by themselves, could be poisonous, but combined together, we put it on our food. Okay, so those two elements form a different compound with different properties from themselves. Okay, here's another example of that. Water. When you combine hydrogen, a gas, and oxygen, a gas, we get water, a liquid, with completely different properties than what we're used to. What we're used to from hydrogen and oxygen. It has completely unique properties. Okay, so compounds give us a lot of different combinations. Okay, we usually represent them with their symbols. Okay, So hydrogen, for example, here's water, H2O. Water has two hydrogens and one oxygen atom in it. Okay, so the symbol for hydrogen is H, the symbol for oxygen is O. We have two atoms of hydrogen represented by this subscript and one atom of oxygen. Okay, so two hydrogens, one oxygen gives us water. So when we want to write water, we write it like this, H2O. That shows us its chemical formula and which elements it came from. Okay, so any type of compound is also going to have some type of chemical formula that shows which elements it uses and the number of elements in that compound. Okay. Then we watch kind of a cheesy British 90s video about elements and compounds. If you want to watch it, it's here. It does a good job of showing the different types of elements, but it's kind of funny to see the 90s music and the 90s clothes. But anyways, if you want to watch it, it's right here. Then we answer this question. So if you are making up participation, please answer this question. Which of the following are elements and which are compounds? So look at each one of these different substances and tell me which ones are elements and which ones are compounds. Okay. So after you've done that, let's move on. So next question is, what is a mixture? Okay. So here's some mixed candy. Here's lemon drink. Okay, both of these are mixtures, and they're mixtures, not compounds, because we are not chemically combining these substances. So the definition is, for a mixture, it's a combination of atoms that are not chemically bonded. Okay, so compounds, they are chemically bonded. They form a new substance, whereas in a mixture, it's kind of just both substances put together, but they just react as separate things. So for example, salt water. Okay, salt water or seawater has this much water in it and this much salt. Okay, and so it is a mixture of water and salt. Okay, and it still holds the different properties though. Salt still behaves like salt, the water still behaves like water. It doesn't form a new compound when it does this. We can continue to categorize the different types of mixtures. So some mixtures are called homogeneous mixtures, and the other ones are called heterogeneous mixtures. Okay, so homogeneous mixtures or homogeneous mixtures are mixtures that have the particles in a way that they are not distinguishable. So for example, if you mix Kool-Aid, okay, you can see that the color of the water has changed red, but you can't see the individual powder particles moving in the mixture. Whereas, for example, some Italian dressing, okay, the particles are distinguishable. It's heterogeneous, so you can see the little spices and herbs and everything inside the dressing. Okay, so homogeneous, you can't see the particles, and heterogeneous, you can see the particles. Okay, hopefully that makes sense. We can continue to categorize into three separate categories of mixtures. There's solutions, colloids, and suspensions. Okay, so this table kind of summarizes all the different parts of these three different types of solutions, but the main difference between the three is the particle size. Okay, so solutions have very small particle sizes, colloids have medium size particle sizes, and suspensions are very large particle sizes. Okay, so if we, for example, look at salt water or Kool-Aid, okay, those are solutions because the particles are very small. The solution or the mixture is homogeneous or homogeneous. Okay, we can't see those individual particles. And if we tried to filter the system, okay, try to separate them again, separate them into, salt and water, or separate them into the Kool-Aid powder and the water, we'd end up with just Kool-Aid again. We can't separate the particles from the substance once they're in the mixture. Okay, so that's a solution. Then colloids, they're very similar. Okay, they have medium sized particles. They are homogeneous. Okay, and sometimes or most of the time you can filter them. So think about muddy water. If I put muddy water through a filter, I could filter out the water and the dirt into two separate pieces. Okay, so even though it started with dirt and water, they're in the mixture, I can separate them back out. Okay, colloids often settle, or the dirt will eventually fall to the bottom, the water will come to the top, type things, or when you put them through a filter, you will get them to separate. Okay, so that's the only difference between solutions and colloids. Is solutions are not filterable, whereas solutions are not separable, and colloids are. So again, other examples of colloids are things like milk. You can separate the fat from the milk. You can look at like ketchup or mayonnaise, those types of things. You can get the oil to kind of separate from the rest of the substance. So again, those two types of things are filterable. Okay, so solutions, homogeneous, non-filterable. Colloids, homogeneous, are filterable, or most of the time are filterable. Okay. Then the last one are suspensions. Okay, very large particle sizes, heterogeneous. Okay, easily filterable. Right, I could easily filter out the herbs from the rest of the dressing. Okay. All right. So then again, if you're answering this for participation, answer this question. Excuse me. Mark each as a solution, colloid, or suspension mixture. So look at these different substances and try to separate them into solution, colloid, or suspension. Okay, so after you've done that, let's move on. So let's just quickly review vocabulary. Okay, so an element is the pure substance. Okay, can't be combined to make a new element or anything like that. These things are pure substances, have to be naturally found. Okay, compounds are combinations of elements, or chemical combinations of elements, whereas mixtures are non-chemically bonded versions of elements and compound. Okay, so pure substance, chemically bonded, non-chemically bonded. Okay, that's the easiest way to remember the difference between the three. All right, now let's move on. So then we talked about physical change. Okay, so physical change is a change in size, shape, or state of matter. Okay, so first some examples. We have crumpling up paper, cutting wood, melting ice, changes in temperature. These things all change the physical state of the system without changing the chemical properties. Okay, this paper is still paper. This wood is still wood. The ice melting, it's still water. Okay, it's still going to behave like water. So these types of things change the appearance or something like that, but they don't change the chemical makeup. Whereas chemical changes are changes in chemical makeup and produce a substance with new properties. Okay, so for example, rusting of nails. You get this iron oxide on the edge of these nails. Okay, that's a new substance. It's not iron, it's not oxygen, it's a new substance that's been chemically bonded. Okay, burning wood, you get the ash and the smoke. Okay, those are new substances from the wood. The tarnishing of silver. Okay, that's a new substance. Photosynthesis, the plants change the way the sugars and other things in the stem are formed so that they can actually use it for energy. Okay, they're causing chemical changes. That you digesting food, you make chemical changes to the food you eat so that you can use its energy. Okay, so all these things produce new substances, are chemical changes. Okay, there's also some evidences of a chemical change. For example, the production of a sound, of light, or a gas. Okay, think about an explosion. When something explodes, that's a chemical change. It makes a sound. It has a light with it. Often it produces a gas. Okay, other things like changes in temperature, changes in color, changes in odor. Those types of things will cause or will help us know that a chemical change has occurred. Okay, instead of just a physical change. So if any of these things happen, that's a good evidence that that chemical change probably occurred. If you want a good example of this, just put a little bit of baking soda and vinegar together. Okay, you will see a gas produced, you will see a change in temperature, and you will smell a very nasty odor. Okay, so again, this helps us know that a chemical change has occurred, not just a physical change. So when we see those things, that's a chemical change. All right, and like I said, baking soda and vinegar is a great example of this. Then we did an assignment called the physical and chemical change story. So that should be on the website if you need to do that. And we also did a write your own story assignment. So that's part of your term project. You can, again, look on the details for that online. Also, I forgot to mention we did a physical versus chemical change activity. You can also look that up online and see how to make that up. The instructions will be on there. All right, and then last of all, we talked about conservation of mass. Okay, so the conservation of mass principle says that the amount of mass at the beginning of a reaction must be the same as the amount of mass at the end of the reaction. Okay, so if I burn wood, for example, then the amount of wood I start with should be the same as the mass of the smoke and the ash that's left over. Okay, any type of chemical reaction, if I'm bonding hydrogen and oxygen to water, the amount of hydrogen and oxygen I start with should equal the amount of water I end up with. Okay, sounds pretty intuitive to us that mass just changes form. Okay, it can't be created or destroyed. That sounds pretty intuitive, right? It's just changing into different substances. But it wasn't actually discovered until a man by the name of Antoine Lavoisier came around in the 1700s, okay, during the French Revolution. And he was actually the first to propose that mass wasn't conserved, because back in those days they thought it was lost. Because if you think of, burning wood again, for example, when you burn wood, the ash doesn't weigh the same as the wood. Well, that's because we're not containing the smoke. Okay, and so back then they wouldn't contain the smoke, and they would say, "Oh, we lost some mass because the ash doesn't weigh the same as the wood." But Antoine Lavoisier was the first one to say, "Hey, maybe we should contain the smoke and see if it weighs the same." So he does, and he's able to prove that through a bunch of experiments and very careful calculations that the mass is conserved throughout the process. And this video right here at this address does a really good job of reenacting his proposal. And so I recommend watching that. But that's all we covered in week 2. If you have any questions, let me know, and thank you for watching.